Okay, next we're going to talk about confidence intervals. Confidence intervals allow us then to make an inference from the sample to the population and thus put together this whole picture that we've been talking about in this semester. Let's go ahead and review this picture. So first of all, let me get my red pen out. We have this population of items, and we're interested in certain characteristics of these items called variables. And what we often want to do is look at summaries of those variables, which we call, or numerical summaries of these variables. And these numerical summaries are called parameters. And so far we've mainly focused on one particular parameter, the population mean mu. Since it might be so difficult to get at all the items in the population, what we do is we take a representative sample from that population so that we have a more manageable, smaller set of information to work with. In this sample, we're also interested in particular summary measures, numerical summary measures, such as, for example, the sample mean. The sample mean is what's called a statistic. And then using this information that we have in the sample, what we try to do is draw inferences back to what we're mainly interested in, and that is what's going on in the population. And the way that we draw these inferences, or one way, is through using confidence intervals. So a confidence interval, or just CI for short, is an interval estimate of a parameter with a particular confidence level associated with it. So this confidence level gives us some information about how good this inference is. And so, for example, we might be left with the following situation where we have, let's say, for thinking about in terms of the GPA example, that the mean GPA of all students on campus is somewhere between 2.5 and 2.8, and maybe we might say we are 95% confident that this is true. These are the kinds of inferences that we're going to make, where this 2.5 and this 2.8 are computed using information that we have in our sample. Okay, so let's look at some motivation behind how a confidence interval expression comes about. Well, if you remember this rule of thumb for the number of standard deviations that all data lies from its mean, so 2 to 3. And earlier in the course, we learned that the expected value of y bar is equal to mu. We learned the variance of y bar is equal to sigma squared divided by n, where this expected value of mu would be, let's say, the expected value of y sub I for I equal 1 to n, where n is my sample size. And this sigma squared here is the variance of y sub I. Okay. Now, I would expect then all y bars, if I were to go out and take a sample, calculate some information about it, go out and take another sample, calculate some information about it, or maybe I'm calculating the sample mean every single time. If I repeated this process over and over and over again, so I have a whole bunch of y bars, I would expect these y bars to be within 2 to 3 standard deviations, 2 or 3 standard deviations of the mean. So here's their mean. I'm going to subtract off 2 standard deviation. And here again is the population mean. I'm going to I'm going to add now 2 standard deviations. And if we do a little bit of algebra, look what happens. We can now put mu in the middle. So now what we have is, you could say, maybe some kind of interval estimate of mu. And so we go out and take a sample, get y bar, and now we have this, again, this kind of interval estimate of mu. Well, how good is this interval though? Well, what we could do is combine information that we know from the central limit theorem to give us an idea of how good it is. Okay, so again, the central limit theorem says that y bar has an approximate normal distribution with a mean of mu, variance of sigma squared divided by n. Equivalently, as we discussed in the past. You can think of this in terms of a standard normal. So I subtract off the mean from the y bar, divide by the standard deviation, and then I get a standard normal random variable. So z has a standard normal distribution, meaning it has mean 0 and also variance equal to 1. Well, let's put this into practice then. Now, I know for standard normal random variables, and I could find this using the Q-norm function, and you really should do this to make sure that you can. I know that the probability that z is between negative 1.96 and positive 1.96 is 0.95 for any standard normal random variable. So again, you can use the Q-norm function. You could use the P-norm function to find this out as well. Please make sure you can do that. Now, based upon the central limit theorem, we know that z has an approximate standard normal distribution. So how about we put in what z is here, and then we put negative 1.96, positive 1.96, and then I use the approximate symbol with this 0.95. Again, I do a little bit of algebra, and now I have mu in the middle. I have y bar minus 1.96 times sigma divided by square root of n on the left side. And I have basically the same thing on the right side, but now I use a plus instead. So what this tells me that the probability that mu is between these two values is approximately 95%. Now, it's very, very, very important for you to realize that the reason why I can make a probability statement here is because I'm working with a random variable, y bar. Sigma is not a random variable, it is a population constant. Mu is not a random variable, it is a population constant. And then I choose what I want my sample size to be. So again, the reason why I have that probability statement there is I have the y bar. Y bar is a random variable. Now we have a problem then, because once I actually go ahead and take that sample and I actually compute what y bar is, y bar now is a constant as well. Maybe like with the GPA example, maybe y bar was 3.0. So if I were to put 3.0 in there, I no longer have a random variable. I can no longer make a probability statement. Okay, so the ultimate goal is I want to find what this thing called a confidence interval. I want to have a certain amount of accuracy associated with it. We have this interval estimate for mu, but how do we deal with the fact that once I replace that random variable with what I observe the sample mean to be, I no longer can make a probability statement? How do we get around this problem? Here's how. We adjust our interpretation, you could say. So if I were to go out and take a sample, compute y bar, go out and take another sample, compute y bar, go out and take another sample, compute y bar. Maybe I do this many, 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 many times. And each time I calculate this, let's say that lower limit of that inequality, and then the upper limit of this inequality. I do that every single time. Then approximately 95% of these intervals, where I say I have a lower number, I have an upper number, approximately 95% of them should actually contain the population mean of mu. That then gets into well, what does a statement like this mean in terms of a probability where I have a random variable y bar that will vary from one sample to the next? So now then the interpretation of this. We would expect mu to be within approximately 95% of similarly constructed confidence intervals. This is a standard statement that people make with respect to this interval estimate of mu. The reason why it's called a confidence interval is because of that 95% that's in there. Now, a more frequent used phrasing of what basically what is represented there is as follows. We are approximately 95% confident that mu is somewhere between what I observe, my y bar minus 1.96 times sigma times divided by the square root of n, and that same thing, but now I put a plus sign in there, somewhere between these two values. Notice I do not say probability, though. That's how I get around the fact that with this y bar, when it's lowercase y, now I'm talking about an observed value. And I can no longer make a probability statement about it. Still, this statement here, I mean, I use this statement. This statement's widely used. But I have to admit, it is definitely not as good as this particular statement there. And in fact, I think sometimes making a statement like this actually leads to misconceptions about what statistics is about. Now I'm a statistician, and I know when someone says the word confident, what they're talking about there. So, you know, I don't have a problem with necessarily using it. Perhaps, though, I should maybe use that statement more for those people who are not maybe as schooled in statistics as I am. You can use either kind of statement in this particular class, but again, that first statement is the better one to use. Okay. So I've kind of already said this. So this expression here, where let's actually put it in terms of inequalities there. This expression, where we have a lower limit, we have an upper limit, is called a 95% confidence interval for mu. One could also rewrite this more compactly by saying, or notice I add and subtract the same number from y bar twice. So you could write it like this. It's a lot easier to do that. Okay, now let's look at how we can generalize this from a 95% interval to some other kind of level of confidence, you could say there. Maybe 99%, maybe 90%. And to do that, we need to introduce some new notation. So when I have a lowercase z within the subscript an alpha divided by 2, this is a symbolic way that people use to denote the 1 minus alpha divided by 2 quantile from a standard normal distribution. So for example, if alpha was 0.05, I put 0.05 in there for the Greek letter alpha, and I get z sub 0.025 back. And what that means in a symbolic manner, 1.96. How do I find that? Let me actually, first of all, go ahead and turn my page here, my paper copy. How do I find that? Well, I go back and use the Q norm function like what we've done before. Again, we use Q because we're trying to find a quantile, and we are given a probability to the left. So here's our actual plot of what we're trying to do. The blue line here helps me show that this is where 1.96 is. To the right is 0.025. So you can think of it this way. What's in the subscript is the area to the right underneath a standard normal distribution curve. Because the whole area underneath the curve has to be equal to 1, then we have 0.975 to the left, and thus the 0.975 quantile. So let's talk about, let me actually go into 10 here. Let's talk about how I got this plot. I really think it's useful to draw stuff to scale whenever possible, and so that's why I've done it here rather than maybe just with my pen draw it out so you can see it. Let's just talk about how this plot is actually drawn. So we've seen the curve function before. The curve function allows me to basically do a plot of f of x is equal to something. And the actual example that we used before was x squared. Okay? And with the curve function, I'm going to use the d norm of function as part of the EXPR, the expression argument. D stands for density, normal. And what this is going to give me, if I think in terms of a standard normal, it's going to give me my f of z value, where f of z is 1 over the square root of 2 times pi times then the exponential function. That's what that e represents there. And I can get that in R from using EXP. So negative z squared, that quantity divided by 2. So this expression here, and you can actually do this on your own. Plug in a value of z and see what happens. This expression corresponds to this d norm, this call to d norm. Now I have an x here instead of the z because R requires you to always use an x to represent what's going to vary on the x-axis. Okay, so I want to draw this from -4 to 4 on the x-axis, so my x-axis limits. The color is going to be red. The line width is going to be 2 times the default. I'll put a nice title on the plot, a y-axis label, x-axis label, and this n equal 1,000 corresponds to how R works with this curve function. What R does by default, it will put 101 equally spaced values corresponding to the x-axis, what you've done for these limits, and evaluate whatever you have for the EXPR part of the curve function. Puts in 101 values, and then simply joins then the corresponding, let's say, f of x values on a plot with straight lines. Now, for some curves, you won't notice the fact that straight lines are drawing all those points. But for other curves, you may notice it. So if you increase the number of values that you're evaluating your f of x at, in this case 1,000, those straight lines look like just like a regular curve. So if I go ahead and do that, put a horizontal line at 0 in terms of the y-axis, and this is what I get. Okay. Now you might be looking at that and say, well, I can see some kind of jitteriness in terms of the lines that are going up on the plot. This happens because of the representation on the monitor itself. If you were to, let's say, save this as a PDF file and look at the PDF version of this plot, you will not see that. It will look like a smooth line. Try it on your own. Okay, so now also on page 5 on that particular plot, if you I also draw a line at 1.96. And we've seen this before where we use the segments function, which allows me to join with a straight line 2 points on a plot. Call those points x0, y0, and x1, y1. And so I'm going to draw a straight line from 1.96 and 0 all the way up to 1.96 and what that f of z value would be. Where, in other words, the curve that's on the plot. Going to color in blue, make the line width 5 times the default. And here we go. Now let's do some nice labeling there. So for example, I would like to label that the area underneath this portion of my curve where my mouse is 0.025. The area on this portion of the curve is 0.975. And to do that, I can use a function called text. I'm going to put text on my plot. Where do I want to put it? Well, how about where x is equal to 0, y is 0.15 in terms of the y-axis. I'm going to label it with the value 0.95, make it twice as large as what the default would be. Do a similar thing with 0.025. And those are the labels. And lastly, what I want to do with this plot is that I want to draw an arrow to show this area underneath the curve here is 0.025. And so to do that, I can use the arrows function. Where do I want the arrow to start at? Let's say the x-axis value of 3, y-axis value of 0.08. Where do I want it to end at? Let's say x-axis value 2.5, 2.4, y-axis value of 0.01. Note that I had to try a few different values there to get it to look good. And there's my arrow. Okay, so that's how you can do that plot. Let me jump back over here in the notes. So you might be wondering, well, why do I put alpha divided by 2 in my subscript? You know, I mean, just as easily I could put, let's say, maybe z of gamma, in terms of the gamma letter, Greek letter. Or I could have put z of c or z of u. I could have done that. The reason why you see alpha divided by 2 there is going to be connected to when we formally define this confidence interval, so it can be at any, let's say, level of confidence. So what you will see is that in this interval statement that we're just about to get to, there's actually going to be essentially 2 different uses of this z of alpha divided by 2. And what we're going to do is, in essence, find a negative 1.96 here if I had a 95% confidence interval. And so if you add up those 0.025s, you get 0.05. Or more generally, if you add up the alpha divided by 2 and alpha divided by 2, subtract it from 1, you get 1 minus alpha, which is the area in the middle of that plot. Okay, so now we get to the formal expression for a confidence interval for mu. Y bars are observed mean. We have some variance sigma squared, and we want an approximate, because we're working with the central limit theorem, 1 minus alpha times 100% confidence interval for mu is given by this expression here. This is exactly as what we've seen, except for now we put z sub alpha divided by 2 in there instead. So if alpha was 0.05, you would replace that z sub alpha divided by 2 with 1.96, and we get what we had before, essentially. Excuse me. Now, this all comes from the central limit theorem. So to basically guarantee that this works, generally speaking, we need our sample size to be large enough, let's say greater than or equal to 30. And while I've already used this term before, I'll define it now. We have a confidence level, like we had 95% before. That was our confidence level. It's our assessment of accuracy associated with the confidence interval. In a general sense, we could say that we have a 1 minus alpha times 100% confidence interval. That might seem odd to say at first, but after you say it a million times like me, you'll get used to it. But what does this mean, just to make sure you see? Let's say if alpha was 0.05, I plug alpha in there, do the math, you get 95%. Okay? Now I have the word problem in capital letters. That must mean we have a problem. We do, kind of. Sigma is used in that formula. So sigma is the standard deviation of, let's say, the y's that exist in the population. We don't know what this sigma is in a real-life application. What do? We'll see shortly. Also, what if n is less than 30? Well, it may work this confidence interval still, but maybe the approximation is not going to be as good. Okay, so because of these 2 problems, we will not use this formula. Notice how that is highlighted. Instead, we will use a similar formula based upon the t-distribution. Now, please note, most introductory textbooks in statistics, unfortunately, still have students use the formula that we just got done doing. And then they say, in other circumstances, switch to using this thing that uses this t probability distribution. In the end, just use the t distribution in our class. This new interval that we're going to use based upon this new probability distribution. If you end up using the standard normal distribution, please note I will count off points on a test or any other kind of graded activity. Okay, so let's define the t-distribution. Sorry to mention it without actually defining it yet. Okay, so there's many named probability distributions out there. We've seen the binomial, we've seen the normal, for example. Here's another one. It's called a t-distribution. It kind of has an interesting story behind how it came about and how it ended up being called this. So let's suppose capital T is a random variable with a t-distribution. The mathematical function for it is this right here. It's a lot more complicated than what we've seen before. Real briefly, this gamma here, this actually represents an actual mathematical function that's based upon calculus again. But there's a nice simplification with it. If, let's say, you had gamma of 5, this would be equal to 4 factorial. If you have, let's say, gamma of, let's just be general here, let's call it c, you would have c minus 1 factorial, provided c is an integer. If c is not an integer, then you have to go back to using that expression. Also, in this f of t function, we see the square root of pi. This pi is this universal constant, 3.14. And then we have the Greek letter nu. Let's see. Maybe I didn't actually write it out. I'm sorry. So this is the Greek letter nu, N-U. This is actually has a special name with respect to the t-distribution. It's called the degrees of freedom. We'll learn more about that shortly. It also, similar to what we've seen with other parameters of a probability distribution, it controls the shape of it. So it allows the distribution to change to meet the circumstances at hand. Then in parentheses here, we have 1 plus t squared. So t is a possible value of our random variable divided by nu, and then we take it all to a power. So quite a messy function. But in the end, you can graph it just like any other mathematical function out there. Get a value of t, plug it in, get f of t out. Get another value of t, plug it in, get another f of t out, draw the plot. Okay, so let's, to help you understand what the t-distribution looks like, I have this old Excel file that allows you to examine it relative to the standard normal. So in red here, we have the standard normal distribution. In blue here, we have this t-distribution, and in this particular case, with 2 degrees of freedom. So nu, that Greek letter, is equal to 2 in our expression. And what you can see is that the t-distribution is very similar to the standard normal distribution. Both of them are symmetric about 0. The difference is the t-distribution has more area underneath the tails of the distribution. People often refer to this as having fatter tails. Now, again, area corresponds to probability. So there's more, you're more likely to be on the tails or the farther from 0 with a t-distribution than you are for a standard normal. Now look what happens here as the degrees of freedom increases. You see the blue lines changing, and it becomes closer and closer and closer to the standard normal, to a point where essentially when we have degrees of freedom of like about 30, essentially it's a standard normal. Not quite, but it is very close. Okay. So let's talk about how this t-distribution came about before we get into like finding probabilities associated with it. So the guy who developed is a guy by the name of W.S. Gossett. He worked for Guinness Breweries in Dublin, Ireland in the late 1800s and early 1900s. He was doing some I think quality control stuff with their beer that they were making, and noticed that the normal distribution just wasn't working as well as that they would like. And so what he did was he did some math, came up with this t-distribution idea, and he wanted to publish it. But Guinness Breweries wanted to protect their trade secrets, so they told him no. And so what he did was he did end up publishing it, but he published it under a different name. He published it under the name Student T. And thus that's how then this probability distribution's name came about. It's often referred to as student's t-distribution, or just t-distribution for short. Now, the t-distribution is widely used in statistics. And it's almost like and me as being a statistician, I use it a lot. And it's almost like for every statistician, it's like you need to make a pilgrimage sometime in your lifetime to the origin of where this t-distribution came about, meaning go to Dublin, go to Guinness Breweries. And in fact, I did do that a few years ago. Do note I don't look really good in that picture there because I was still dealing with jet lag. But anyway, in the breweries, they have like the famous people who have worked there. They have like little plaques. And indeed, they have this plaque for W.S. Gossett there. And I think they could have probably made the walls look a little bit nicer, but that's the way it was back then. And if you notice there, he's a chemist, statistician, and down at the bottom of the plaque says student t-test. We'll learn what a t-test is shortly. Okay. So let's find some probabilities associated with the t-distribution. If I wanted to find, for example, the probability that a random variable t is less than 1.96, and suppose the degrees of freedom is 5, how would I find that? Well, I could do some calculus. And I could take an integral. I think I failed to mention this. The value t in the t-distribution is defined between negative infinity and positive infinity, just like what we had with the normal distribution. So to find this probability, I would find the integral from negative infinity to 1.96, plug in the value of nu in there, do the calculus, and I get about 0.95. Okay. Again, we're not going to actually formally do the calculus in this class. Instead, there are nice functions in R that will do it for us. In particular, there is the PT function, probability t-distribution. I put in my quantile of 1.96 there. Instead of saying nu, I have df for degrees of freedom. I put in a value of 5, and that's how I get the probability out. Now, similar to other functions in R, you can use vectors of information with the function. The function will be applied to the multiple elements of the vector. So if I worked with a quantile 1.96 again, and let's say I looked at a whole bunch of different degrees of freedom and did the evaluation, you can see that the probability that t is less than 1.96 is increasing as the degrees of freedom increases. And in fact, it's getting really close to what we would get for a standard normal. If I could somehow put in a degrees of freedom infinity, I will get a standard normal. I will get that corresponding 0.975. So again, as your degrees of freedom increases, as we saw in the Excel file, you get closer and closer to a standard normal. And if you could somehow actually have an infinite degrees of freedom, you will get the standard normal. But what about finding quantiles? What about finding quantiles from a t-distribution? Let's say I want the 1 minus alpha divided by 2 quantile. I could have said maybe I just want a 0.975 quantile, but I'm just trying to be general here. And you'll see how we use this then in our interval statement, why I'm using alpha divided by 2. So let's say alpha is 0.05. Then, using the QT function, I put 1 minus alpha divided by 2 in there. I use the degrees of freedom of 10, and I get 2.228 out. Notice that QT stands for quantile t-distribution. In a similar manner to what I did above, I could look at what happens as the degrees of freedom increases, compare it to a standard normal, and we can see that that quantile is getting closer and closer and closer to what we would get with a standard normal. Now note that most textbooks, introductory textbooks that is, will often include a table of probabilities associated with a t-distribution, similar to what we saw with a standard normal distribution. And those books would spend a lot of time showing the students, well, how do you use the table to find it? But in the end, there's no reason to use a table anymore. Let's just use R or some other statistical software package that does the calculation for us. Okay, so why am I spending time now talking about then the t-distribution? Note that we're on page 11. Well, let's go back to the central limit theorem. So this Z here has an approximate normal distribution for a large sample size n. The problems with this statement, though, is that mu and sigma will not be known in real-life applications. And what if n's small? So a partial solution to those problems is, how about we replace sigma with a random variable, the sample standard deviation. If I do that, and y1 through yn has a normal distribution, meaning my population could be characterized by a normal distribution, then this quantity t here has a t-distribution where the degrees of freedom ends up being your sample size minus 1. Okay, so that's an interesting result. This is basically what Gossett did. He proved that. So I replace sigma with a random variable s, my sample standard deviation that we saw a long time ago. This makes this more realistic because I can come up with an observed value of s from taking a sample. Also, and it should be a capital T there, sorry about that. Also, this capital T, this random variable t, has a t-distribution exactly, provided that we have these normal random variables, or these random variables can be characterized by a normal probability distribution, no matter what the sample size is. Now you might be thinking, well, wait a second, Chris. Now you're adding an assumption to what we're trying to do here. We're trying to get away from having these kinds of assumptions. Well, fortunately, though, statistical research has shown that even if I don't have a normal distribution there, this still can work very well with a t-distribution. And you'll see some examples of why that occurs as we go along in the notes. Okay. So suppose n is large, though. What happens to this probability distribution of t? Now remember that degrees of freedom is n minus 1. I don't know, maybe the answer is too obvious, but I'm not going to answer it here. I want you to think about it and ask me if you don't know what the answer is to this. But as the degrees of freedom increases, what should happen to a t-distribution? Well, now put this in the context of the sample size. Then think about the central limit theorem and what we know about that. Okay, so let's talk about some notation. Excuse me. So, similar to what we had with z of alpha divided by 2, we will often want to symbolically denote a quantile from a normal from a t-distribution. And the 1 minus alpha divided by 2 quantile from a t-distribution with n minus 1 degrees of freedom is denoted symbolically like this, where we have a little t subscript, we put alpha divided by 2, and then a comma, n minus 1. We need that n minus 1 there because that's going to change what the distribution ends up being. So we need the n minus 1 there. And for some reason here, I decided to draw it out instead of actually do it in R. But this is essentially what's going on here. We are finding what number relative to a t-distribution has an area of alpha divided by 2 to the right of it. We can then write, for example, a statement like this. The probability a random variable t is between the negative of this quantile and the positive of this quantile is 1 minus alpha. Okay. Now finally, then we get to the confidence interval that we actually will use in this class for the population mean. So a confidence interval for mu, but hey, I don't know what sigma is. So here's what it looks like. This is a 1 minus alpha times 100% confidence interval for mu. It looks very similar to what we had as a result from the central limit theorem, excuse me, except for we replace the value from the standard normal with the t-distribution value, and we replace that sigma with the observed sample standard deviation. So what we actually calculate from the sample. Okay, so where does our confidence come from that this actually works? Okay, so similar to what we saw before, we can write this probability statement relative to a random variable t. We can replace t with the expression that we saw before, do a little bit of math so that we just have mu in the middle, and voila, we have our probability statement relative to this, and we have a 1 minus alpha probability. Notice there are two random variables in here, y bar and s. Okay. We will talk about the ramifications of that coming up. So what if n's greater than or equal to 30 here? Is there much difference between the confidence interval that we just stated versus the one that we had for using the central limit theorem? In the end, there's not going to be much difference in terms of an actual calculated value. Because remember how the t-distribution is going to approach a standard normal as the sample size gets large enough. Also, you can think of it this way. Well, we normally don't know what sigma is, but let's say we did. Well, our sample standard deviation, as that sample size gets larger and larger and larger, is going to become a better and better and better estimate of sigma itself. So in the end, our interval that we had before, with the based upon the central limit theorem, and the interval that we have now are going to be very similar. That's why whenever I teach an introductory stat course, I say, well, let's not even worry about that other interval. I'll introduce it to motivate this interval that we use based upon the t-distribution. But let's just go with this. It's going to be easier. Okay, so the confidence interval does require the normal probability distribution for y1 through yn. That's how we get this t expression. But I've kind of already said this before. Often I give exercises to students to actually demonstrate this on their own so that they don't just take my word for it, but they can see that indeed that this is true, and that is statistical research has shown that this confidence interval still works well for most other probability distributions for the y's. Now, there are other confidence interval equations that you could use. We won't talk about those in this class, but this particular interval that we're looking at is widely used all over because it is very good. It works well. Well, what do I mean by it works well? Well, this is what I mean. Suppose I go out and take a sample, calculate y bar, calculate s, calculate my interval. Suppose I go out and take another sample, do the same thing. Suppose I go out and take another sample, do the same thing. I repeat this many, many, many times. What you will find out is that 1 minus alpha times 100% of those intervals that you've calculated will contain the population mean. That's what I mean by it works well. And it works well pretty much no matter what your y's, the underlying distribution is. And even if you have some really weird, funky distribution for your y's, funky is not a statistical term, I'm just making that up. If you have a large sample size, it's not going to matter then, because that central limit theorem essentially kicks in, even though we're not using the central limit theorem. But again, our interval is going to be close to what we got with the central limit theorem anyway, because of the relationships between the t and the standard normal. Okay, so again, and you're going to see me repeat myself a number of times here because I've taught this type of course many, many times, and I understand where students struggle. And I try to then, in my notes, counteract those struggles by repeating things or trying to explain things in a different way. And so understanding that confidence level is something that can be difficult. And so I just want to repeat our interpretation of this interval then. We have two possible interpretations. We would expect mu to be within approximately 1 minus alpha times 100% of similarly constructed intervals. Okay. Or we are approximately 95% confident that mu is within the interval. Again, I do not say probability. If you ever would say probability there instead of confident, that is wrong, and I will take off points for it. But these two interpretations here, you can essentially use them word for word on any kind of graded test or other graded item. Just phrase it in terms of the actual problem. So if I'm talking about, let's say, GPAs, phrase it in terms of the GPAs. Okay, so let's take a look at an example. So this example deals with light bulbs. You know, when you buy a package of light bulbs, very often it will give you some value for in terms of how long would one expect the light bulb to last. Suppose for a particular kind of light bulb, it's actually probably not a very good light bulb, but let's say it's a light bulb of interest. Suppose the company is interested in estimating the mean lifetimes of its light bulbs. The company takes a random sample of 16 light bulbs, that's our N, and finds that they last on average about 299.2 hours with a standard deviation of 80 hours. Based upon this information, let's find a confidence interval for what the true population mean of all the light bulbs would be. Okay. So y sub I for I equal 1 to 16 are random variables denoting the lifetime of the ith light bulb. When we actually observe how long they last, we get the little y's. And based upon that, we can calculate a sample mean and the sample standard deviation. We're going to be interested in a 90% confidence interval. So that means alpha is 0.10. That will help us then find our quantile from a t distribution. We need to find the 0.95 quantile with 15 degrees of freedom. I can go to my QT function to do that, and I get 1.753. So let's calculate the interval then. Here's my expression for the interval. I put in the mean, I put in the quantile from the t distribution, I put in the standard deviation, and I put in the square root of the sample size. And I get 264 is less than mu, which is less than 334. That's my interval. That's how I could state it. I could state it another way as well, where I say left parentheses 264, comma, 334, right parentheses. So I go from 264 up to 334. Mu is somewhere between those two numbers. Note that I do not write it like this. That doesn't make sense. We always go from the smaller number up to the larger number. So don't do that, please. Okay, so let's look at how we do these calculations in R. Let me get to my program. Okay, so I type in y bar, s, alpha, and find my quantile. Let's go ahead and do that. Then let's find the interval. I take y bar minus the value from that t distribution times s divided by the square root of n. So I do that for my lower limit of my interval. For my upper limit of my interval, I use a plus. I put lower and upper into a nice data frame for display purposes, and there you go. There's my interval. I could also do then a plot of my interval. And this is what my plot looks like here using the plot function as we've seen before. Now, this plot's okay. I include the plot in the function code for something that you'll see is important later on. Okay, so now we've done the calculation. And in an introductory stat course, or actually any stat course, I guess, what's important to do is that now that you have this numerical calculation, how are you going to use it? And you need to be able to use it properly. So always on a test, or generally speaking on a test or other graded assessment, I will always like to put an additional question beyond doing the calculation and basically involves you needing to interpret that interval in some way. So the question is, could the company advertise that their light bulbs last on average 250 hours? Explain. Well, let's look back here. The interval is 264 to 334. I'm 90% confident that mu is actually between those two numbers. So can I advertise it's at least 250 hours? Yeah, I can. Because the whole interval is above 250. Okay. Now, I have set up our program to help you investigate what happens when you change maybe y bar. Maybe you change the sample size. And then this plot, corresponding plot, will update relative to that. And I expect you to go to this program and do some investigation so that you can start getting an intuitive feel for what will happen. So for example, we'll step through something here, step through an example. Let's say instead of a sample size of 16, suppose I took a sample size of 160. And for demonstration purposes, let's just say my y bar was exactly the same. My value of s was exactly the same. I'm still going to find a 90% interval. Well, what's going to happen to this confidence interval? I want you to think about this both from an intuitive standpoint and also a mathematical standpoint. Let's look at the math part first. Okay, let's find the formula. Okay. So we are changing this part of the interval from 16 to 160. So what's going to happen with 1 over the square root of n as n increases? Well, that's going to cause 1 over the square root of n to dramatically decrease. So if this number, let me actually do some erasing here. So this number here is going to go down. Now I'm still going to, and then I'm going to multiply it by this number here. Now remember, as at t distribution, the degrees of freedom for the t distribution increases. T becomes increasingly more like a standard normal. So what that's going to mean, and again, we can take a look at this, this file here. Notice how for a lower degrees of freedom, there's more area underneath the tail of the distribution. And if we think of trying to find, let's say, the 0.95 quantile, that means then we're going to have to go farther out on that right side of that distribution, meaning the value of t is going to be larger to get that quantile. But as that sample size gets larger, look what happens. Now the tails of the distribution go in, and therefore I don't have to go out as far on that distribution to find the quantile that I need. So what that means then for us is that this t distribution value is going to decrease as well. So I have a smaller number here, I have a smaller number here, and I'm going to add and subtract it from y bar. So what's going to happen to mu then? I'm sorry, what's going to happen to the confidence interval? It's going to become narrower. It's going to be a smaller range, you could say. So let's actually try it. Oops. And there's my interval. I don't know what happened. I guess I'm missing a particular line on there. Or I'm sorry, I know what I did. I should have opened up the graphics window. Of course, it went to a different monitor. And now compare this interval. Look how short or how narrow it is compared to what we had before. So that's the mathematical reason behind why this occurs. An intuitive reason is that now I have more information about my population by taking a larger sample. Since I have more information, in order to be 90% confident, I can probably go with a shorter, a narrower interval, because now I'm more confident about this y bar that I got there as an estimate for mu. So that's the intuitive explanation behind why that interval gets smaller with a larger sample size. But again, I want you to come up with like an intuitive explanation, also a mathematical explanation for what happens if, let's say, if the sample size decreases, suppose alpha changes, suppose the standard deviation changes, and so on, so that you get a good feel for this. We will be doing confidence intervals now for the rest of the semester, so the time that you put into understanding the confidence interval now will go a long way later in the semester. Okay. So we are on page 14. So the confidence interval estimates mu. With 90% confidence, mu is between 264 and 334. And again, I'm repeating myself. This does not mean the probability of this one interval that contains mu is 0.9. That is not what that means. And it all comes down to the exact same reasoning that we had before when we were dealing with the central limit theorem and its corresponding interval. Once you replace the random variables with their actual observed values, you no longer can make a probability statement about that particular interval. Okay. Now, our interval again was, let me actually write it out here, 264 to 334, the mean lifetime of these light bulbs. Let's say, though, instead the confidence interval was all below 250 now. Then the company could not advertise that their light bulbs last at least 250 hours on average. The reason being is because, you know, our evidence from our sample, let's say maybe it was, let's say 230 to 240. The evidence from our sample now says actually the mean is somewhat lower than that, so we can't advertise it. But what if, though, the confidence interval actually contains 250? Maybe the confidence interval was 240 to 270. Could we advertise that the mean lifetime of these light bulbs is 250? Well, this interval means, well, the mean lifetime could be 240, could be 245, could be 250, but it could also be 255. It could also be 270. So could we advertise it? No. So we cannot, because it could be less than 250. It could be greater than 250. So let's take a look at another example. This goes back to our wind speed example that we've had before. And what we like to do is find a confidence interval for the population wind speed. I want you to think about what that actually means in the context of this particular sample. So first of all, though, do you think the wind speed has a normal distribution? Well, we've seen previously that it sure doesn't look like it's a normal distribution. It looks like it was right skewed. So the answer is no. But should we be worried about that then relative to this confidence interval that we're using with the t-distribution? And the answer to that is also no. We shouldn't be worried because we have such a large sample size. we don't need to worry about that. Again, that relates the t-distribution interval to the the central limit theorem version of the confidence interval as well, and all those discussions that we had earlier. So let's look at how we can find now the confidence interval. Okay. So you need to read in your data into R, check to make sure it looks okay. And let's actually find the interval. So I'm going to use the mean function to find the sample mean, the SD function to find the standard deviation, state alpha, let's say I want a 95% interval, and find my sample size by looking at the length of all my wind speeds. Then I find the interval exactly the way that we did before with the light bulb example. So let's go ahead and do that. And so my interval is 9.46 to about 10.94. So I'm 95% confident that the population mean wind speed is between these two numbers. Again, another way to phrase the interpretation is that in all similarly constructed intervals, I would expect 95% of them to contain the population mean wind speed. Okay. So that is about on page 19. As you might imagine, since I put, oh, here's the longer way as a comment, there's going to be a shorter way. And indeed there is. Here's the shorter way. There's an actual function in R that will do the calculation for you. It's called t.test. The word test will be explained when we do the next kind of inference method called a hypothesis test. The first argument is, well, where's your data? And my data is in the y, it's the y variable of wind. And I want to use a confidence level of 95%. So I use the argument conf.level. How did I know it was called that? Well, take a look at the help for t.test. And let's go ahead and run that. And here we go. Now we get some other results here that for now we're not going to take a look at. We will later. The thing I just want to concentrate on is this thing called the 95% confidence interval in the output, and that's exactly what we had before. So you can see how simple that is. So this is on now page 20. So again, a follow-up question. Or first of all, let's make sure, here's again how you could state what the confidence interval is. Then again, I like to have some kind of follow-up question that makes you interpret what the interval means, so you're not just thinking, okay, I got the numbers, that's it. Suppose an electric company is trying to decide on building a wind turbine at the same location where these wind speed readings are taken. They need the wind speed across all days to be greater than 9 miles per hour in order for the wind turbine to be profitable. And let's say we're just dealing with the February wind speeds. Should they build the wind turbine? Explain. Well, the answer is yes. Notice the entire confidence interval is above 9. Okay. Now, let's look at how we can save the results from t.test so that we can maybe use those results at a later time. Now, t.test actually produces a lot more information than what was displayed to the screen. And if we say save.results gets the results from t.test, we can just type save.results and we see basically a summary of what's in there. But if we say names save.test instead, or save.results, excuse me, now we have a list of all the items that are actually in there. In fact, in R's terminology, t.test creates a kind of object called a list. And we've actually seen some lists in other places. We haven't necessarily said it before. So for example, our data frame that we had before was a list too. And anytime that you have a list, and you can use the names function with it and see what's inside of that list and pull information out. So for example, if I say save.results $conf.int, hey, there's my confidence interval. This will be useful for us when we want to do some additional calculations with these kinds of results. but I just wanted to show it to you now. Note that what comes back to you in terms of conf.int is actually a vector. So if I just want the first element of that vector, I put a 1 there. If I want the second element, I put a 2. Okay. Page 21. So we haven't talked about, well, how do you decide what confidence level to have? You know, should I use 90%? Should I use 99%? Should I use 99.99999%? What should I use? Well, you might be thinking, let's use as high as possible because we want to be as confident as possible. Unfortunately, it's not that easy. Before I get into that, though, typical levels for a confidence interval are used in practice are like 90%, 95%, and 99%. Why? Well, it's a lot easier to say than, let's say, 94.1234566666666%. Okay, simply that's why. And obviously, it's a 90 and above is a pretty large number. Now, the reason why you don't necessarily want to go up to, let's say, a 99.99999% confidence interval is because your confidence level is directly related to the length of the interval that you have. And what I mean by length, I'm talking about taking your upper endpoint of your interval and subtracting off the lower endpoint of your interval. In summary, the higher the confidence level, the wider the interval. The lower the confidence level, the narrower the interval. Well, why? Again, you could go back to the actual confidence interval expression. So y bar plus or minus the value from your t distribution times s divided by the square root of n. Excuse me. As your confidence level increases, that means alpha goes down. And what that's going to mean for this t distribution value here, that is going to go up because you need to get farther and farther and farther out on that t distribution. And as that number goes up, then that's going to mean then I'm going to have a larger number here on the right side that I have to add to y bar or subtract from y bar. And that means the interval is going to get wider. Now, on your own, you should think about, well, what happens as alpha goes down? What's going to happen to my confidence interval? It's going to become narrower, but make sure you understand why. Now, also, we will like the confidence interval to be the shortest in length as possible, but still have a high level of confidence. Well, why? Let's take a look at this example to explain it. Okay, so this is the light bulb example once again. The length of that interval was 70 about. But let's say we were given the choice between two different confidence intervals. The one that we had before and another one that is from 299 to 299.4. And let's just say somehow they have exactly the same confidence level. Well, which would you choose? Well, choose the one that is narrower because it gives me a shorter range. I have a shorter set of numbers to think about in terms of what that mean population lifetime would be of that light bulb. So that's why we want an interval as short or as narrow as possible. How can we do that, though? How can we get as narrow as possible interval? Well, this goes back to thinking about an intuitive explanation of this interval, what happens with it, and also in terms of the math part. And we've kind of done some of this already. I could take a larger sample size. So again, and we actually went through a demonstration of that. As my sample size goes up, 1 over square root of n goes down. Also, my t distribution value decreases as well. And what's going to happen is that everything on the, I'm going to add and subtract a smaller number than I would have had before with a smaller sample size. And this demonstrates this here. But of course, there are disadvantages of taking a larger sample size. Like with light bulbs, if I take a larger sample size, each of those light bulbs will eventually burn out because I'm going to have to watch them until they actually do burn out. That might be a good job for a grad student. That's supposed to be a joke. Anyway, but now I can't use that light bulb anymore. So I've destroyed that item. And so that's going to cost me money. Obviously, light bulbs don't cost that much, but you can think of other situations where the larger your sample, the more money it's going to cost. Think of it also in the terms of, let's say that we were trying to sample people. Well, it costs money to, go from, let's say, a sample size of 100 people to a sample size of 1,000. And as you might expect, it will take more time. It would take more time to sample 1,000 people than 100 people. Well, what's another way that you can make the interval more narrower, or decrease the width of the interval? Well, lower your level of confidence, because this value here is going to go down. Try it out on your own, verify that indeed that does happen. Of course, there's a big disadvantage, and that is now you're less confident. So let's say, for example, with the light bulb example, I went from a 95% interval to an 80% interval instead. Or I think before I had actually I was dealing with a 90% interval. So before this was 90%, this is now 80%. And look at how this value for the t-distribution now has decreased. And that causes the interval to be shorter in length. But the problem is, now I'm less confident. So, again, examine this lightbulb.r program further so that you get a better feel for what happens in these kinds of situations. Now, lastly, some final notes about confidence intervals. Excuse me. Oh, what is a 100% confidence interval? Could one be found? No. I guess for any problem, I can give you an interval of this. Negative infinity to positive infinity. That's my 100% confidence interval. Is that useful at all? Well, no. And lastly, well, let's, again, think about what a confidence level means in terms of this repeated sampling context. Suppose, again, that I have a 95% confidence interval that I want to calculate. So I go out and take a sample, I calculate the interval. Suppose I go out and take another sample, calculate the interval. Suppose I keep on doing this a lot of times. Maybe I do it 1,000 times. Since each of them are 95% confidence intervals, that means approximately about 950 of them will actually contain this value of mu. 50 of them will not. That's how you interpret then the confidence level. An individual interval itself does not have a 95% probability that it works, meaning it contains the population mean. And lastly here, this is something if you want to examine on your own, you can. I'm not going to test you about it, but this talks more about this concept of degrees of freedom and where it comes from. So that now concludes then this section on confidence intervals.